Hi, this is Roger from Labs, and today we'll make some measurements of the Q factor of some AM magnetic antennas. Except for the 5 different loopstick antennas you can see here, I still have my 2 spiderweb or spiral wound, or what else are they called, basket weave coils. And what at the moment is not in the picture is our frame antenna here. Now, in the past I've made a lot of videos about how to calculate the different antennas, the Q factor, the losses that we have. And we have discussed a lot about the inductance and anything else. But now comes the test if all of our thoughts, ideas and formulas, if they really meet the reality. But we have to take some precautions when measuring Q factor. I've done a separate video about the method that I use, and we will discuss this in a minute, once again in a short form. One precaution beforehand. You might think if you have an LCR meter, which does in fact can display the Q factor, that, well, just let's take my LCR meter and measure the Q factor. Well, that gives no meaningful results, because your LCR meter can only measure the Q factor at the specified frequency, which usually, even with good LCR meters, is a maximum of 100 kilohertz. But here we are dealing even in the long wave range. Here you can see 3 combined long and medium wave ferrite-rod or loopstick antennas, while this one is a special type I've wound for myself for the medium wave, and this one is for short wave reception. Anyway, we have totally different frequencies. Even the long wave range centers at 200 megahertz, and the medium wave centers at 1 megahertz. And you cannot, with any kind of formula, try to correct your result that you get from your LCR meter. So an LCR meter is totally useless for measuring Q factor outside the measurement frequency. And all of these coils are designed for much higher frequencies than a normal or even a good LCR meter can measure at. So you will hardly possess an LCR meter which can measure at 1 megahertz or 3 or 5 or 10 megahertz. But there is a simple method, and let's just, before we start with the measurements, just shortly discuss how we are doing it, how you can do it for yourself, but what you have to watch out for and which precautions you have to take beforehand. So the first thing we're gonna do is build up a tank circuit out of one of our test coils and a variable capacitor, and of course we take one of these air isolated capacitors, not one of the cheap and small plastic film variable capacitors, simply because the plastic film variable capacitors introduce losses of their own, while the highest quality capacitors are these air isolated variable capacitors. So not to give any wrong value due to losses in the variable capacitor, we just want to measure the losses in our reception coil, not these losses. We're using these air isolated variable capacitor. That's the first precaution we have to take. Otherwise, measuring above a Q factor of 100 will become difficult or impossible, because you don't then measure the losses here, but you measure the losses here. The next thing we do is we couple a square wave from a signal generator of the frequency doesn't matter, let's say something around 1 kilohertz, it could also be 100 hertz. But now comes into play our tank circuit here has an internal resistance, and that is called the resonance resistance. And if we would directly couple our frequency or signal generator to our tank circuit with usually 50 ohms output impedance, then our tank circuit would be shorted out via the 50 ohms. And this of course may under no circumstances happen, so we have to take a high impedance resistor. You could also take a capacitor, but there's a reason why I'm taking a resistor to couple our square wave into our tank circuit. And we will later see that the coupling resistor should be in the order of 1 to up to 10 megohms. Now the second thing is, of course, we now have to measure our output signal. What the square wave does, it excites our tank circuit once every, if we take a 1 kilohertz square wave, it would excite our tank circuit twice every millisecond. Why twice? Well, on the rising edge and on the falling edge. We could also use the sync output of our signal generator just to go to the trigger input of our oscilloscope. And what we get now here is just a dampened oscillation, and we tune our variable capacitor. So a dampened oscillation looks like this. You first get a step response, and then you get your sine wave, and it slowly dampens out, and that's what we want to see on our oscilloscope. So we have to couple our oscilloscope also, and with the usual oscilloscope probes we have either 1 megohm or 10 megohm input impedance, and this is also important because this is the second load we put to our tank circuit, and this load should of course also be in the order 1 to 10 megohms, so a 1 or 10 megohm switchable oscilloscope probe is quite suitable because it has exactly the right range. You mustn't have a digital storage oscilloscope. You can just as well use an analog scope, but it's quite helpful to connect the sync output of your function generator with the trigger input so that you get a stable view of the dampened oscillation, and only on one of the two edges, either the rising or the falling edge. Otherwise the two dampened oscillations would overlay and the screen picture becomes a little bit difficult to interpret. And of course we have to tune our tank circuit with our variable capacitor for each antenna, for each reception coil we want to compare to exactly the same frequency. So we will use 200 kilohertz for the long wave AM radio, 1 megahertz as which is the center of the medium wave AM radio, and we will try our shortwave ferrite-rod antennas at, well, let's say 3 different frequencies, 3, 5 and 10 megahertz for our shortwave ferrite-rod or loop stick antenna. So here we see the test setup, or 90% of it. Here from the left comes in our 1 kHz square wave, which excites our tank circuit. It comes in here at this red alligator clip. Then comes the 10 megohm coupling resistor, and then the green lead goes to the tuning capacitor, and in parallel is, in this case, a ferrite-rod antenna with a long wave coil, and we tap off directly at the coil or at the connection of the LC circuit with our oscilloscope probe, also set to 10 megohms, so for not to give wrong results due to loading the tank circuit just with neither the impedance of our function generator nor with the impedance of our oscilloscope probe. So we have two 10 megohm resistors in parallel, 10 megohms from the oscilloscope probe, 10 megohms as a coupling resistor from the function generator, which gives a total load of course, 5 megohms. And here you see with 1 millisecond distance, the dampened signal. If we enlarge it a little bit, we can first of all measure the frequency and tune to the same frequency for all our coils. So we will measure the long wave coils with 200 megahertz, and I'll show you an interesting effect. Oops, just seen here we already have either a coupling in a you can see that it's oscillating here, and there must be a broadcast station, could be BBC. So you can see, we have to watch out. You can see the signal pumping. Either that's a spurious signal here coupling in from the PC or from anything else, perhaps even from the photo floodlights. But it could be also a broadcast station. So we have to watch out because I think BBC broadcasts at 198 kilohertz, so 200 kilohertz is probably not the best idea to compare, because then you can see here we don't get a stable signal, because in the end we want to count the number of cycles where the amplitude drops to half of its peak value. And if we have such an oscillating signal due to a broadcasting station that is exactly at this frequency we want to measure, then it becomes a little bit difficult, even if to get a little bit clearer signal. If we go to averaging mode, that won't help a lot, or well, a little bit, to get a more stable and more clean signal. So, but you can see here, even without the exciting signal, we still have a remnant of the dampened oscillation here on the left. So anyway, two things to do. First of all, we have to get to exactly our measurement frequency, or we have to tune to the tuning capacitor to 200 kilohertz. Perhaps we'll change to 250. Let's see, we have 1 microsecond per division. That's at the moment 1, 2, 3, 4, 5 micro. Yeah, that's relatively near to 200 kilohertz. So this is more exactly at 200 kilohertz. So first of all, we have to set with our coil, with our tuning capacitor, the exact equal frequency for all our coils, because it would be unfair to measure them at different frequencies because the Q factor varies with the frequency. And now I'll crank up the zoom of the camera a little bit so that we can concentrate onto the oscilloscope screen. So, okay, now I've made the settings that way that, first of all, that the amplitude here is in a way that it starts at exactly 4, I just had to adjust it a little bit, at exactly 4 divisions here, and then we just count the number of oscillation until this goes down to exactly half its value. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4, 5. So there were around 25 cycles. Just it varies a little bit, so it's not that easy measuring Q factors above 100. Let's try it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. Yeah, it's 25 cycles. Take that number by 5 and you get a Q factor of 125 at 200 kilohertz. So this is a very good result. Such a high Q factor for a long wave coil is quite okay. So, and now let's change to our next coil. So, next is the long wave coil of this slightly larger ferrite rod antenna of Russian origin. So we are counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4, 5, 6, 7, 8. 28 or 29, let's say 29. So this gives a slightly higher Q factor of nearly 150, or to be exact 145. You can see it's quite difficult. Any movement I make here influences the tank circuit. I'm just moving my hand now near, and you see it takes some time for the signal to recover because I've set the averaging rate to 1024, and so you should count twice. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 1, 2, 3, 4, 5, 6, 7. Yeah, it's 29 or 30, so Q factor of nearly 150, which was also what I was expecting, simply because the Litz wire here in this coil looks like a better type than the one we just saw before, and the kind how the winding is done so that you have some layers which crisscross each other is also good for having not too much proximity effect that could diminish your Q factor. So this is a little bit better than the small one, and now let's come to the next coil. So next is this ferrite rod long wave coil with a coupling secondary winding. Of course we only use the primary. So I've tuned it to 200 kilohertz again, and now let's see what Q factor we get. So we're counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4. So around 24 cycles times 5 gives us 120. So until now, all the 3 ferrite rod antenna were in the range higher than 100, between 120 and 145. And now let's compare this as the next example with our spiderweb coil for long wave. And we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Only 13 cycles times 5 gives a Q factor, which is a lot worse than we've measured before, of only 65. Now I already have an idea why this is so. Let me count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. Yeah, 13 or 14. The reason is because we don't have a ferrite rod here. We need a lot more wire. So the total length of the wire, even though it's Goodlitz wire, is very much longer than, for example, here on our small ferrite rod. And this gives simply a higher ohmic resistance, and this ruins the Q factor. But you cannot use thicker and better Litz wire simply because you're running out of space here. So for long wave, apparently, at least concerning the Q factor, the spiderweb coil is not the best, but the ferrite rod antennas were better. Astonishing. So now I've put the frame antenna to our test setup. There we made a little trick. The basic reception coil does not have an inductance in the range of 2 millihenries as the other coils, but it's the inductance of the medium wave coil. And then we just added for the long wave range a fixed inductor of 1.8 millihenries, so that in the end the total inductance is the right value for the tuning, for the same tuning capacitor, but the reception coil is only the medium wave coil. So now let's count our cycles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, around 22, which gives a Q factor of 110, and that's around in the range of our medium wave, of our ferrite rod antennas. The reason why here the frame antenna is not better is simply it was optimized for the medium wave range concerning all parameters, and just by adding a fixed inductor with I think 6 ohm or so ohmic resistance, series resistance, this does not give an ultra high Q factor on the long wave range. But this is not necessary, because a Q factor of 100 in the range of 100 gives you only a bandwidth of 2 kilohertz. So it's even, basically it's even too high. When we load this with a crystal radio, so with the same resistance as the resonance resistance of the coils are, then the Q factor always halves. Then we would get a Q factor in the range of all of our antennas between 50 and 80, no, 50 and 60, and that would give a bandwidth of between 4 and 5 kilohertz. That is quite the right value. So on the long wave range, a too high Q factor, as I explained in another video, would even be detrimental to your listening experience. You get an ultra high selectivity, but not all of the audio frequency band is included in, because the bandwidth is so small that the higher audio frequencies are cut off or lost in the bell-shaped curve of the frequency response. So let's sum it up. The ferrite rod antennas give surprisingly good Q factors, but this is not the worst. In this case was our spiderweb coil, but this is not the last word, because the total reception result is not only Q factor dependent. You also have to multiply this with the cross-sectional area, and later we will try to measure the true sensitivity of all our coils with a little of kind of transmitter that I've set up here, but I'm not sure if we get really comparable results, because it's quite difficult to build up a long wave or medium wave transmitter, which is not only a few centimeters but a few meters away. Let's go over to the medium wave coils.